Starting from this lesson up to a few more lessons, we will be learning about the limit of a rational function. So for that, let's consider an example of a rational function. We know that a rational function is a ratio of two polynomials. So suppose it is defined as x squared minus 3x plus 2 over x squared minus 2x, where you can see that the numerator as well as the denominator of this expression is a polynomial. So this is a rational function. Also, this expression is defined if the denominator, that is x squared minus 2x, is not equal to 0. Because in case if this denominator is 0, this expression will be division by 0, and which is not possible. We have learnt it already in the lesson number 3. So if we put this denominator is equal to 0, that is x squared minus 2x is equal to 0, and if we factorize this expression, we will get x times x minus 2 is equal to 0, which implies that x is equal to 0 or x is equal to 2. That is, this expression is not defined for x is equal to 0 and x is equal to 2. Now, as we had discussed the meaning of the domain of a function in the lesson number 1 and lesson number 3, so without going into much detail, I'm going to write down the domain of this function. So the domain of this rational function is the collection of all those values of x for which the denominator of this rational function, that is x squared minus 2x, is not equal to 0. So x squared minus 2x is not equal to 0, and which is same as saying that x is not equal to 0 and x is not equal to 2. Because only in this case this expression is defined. So we are now ready to discuss the limit of a rational function as x approaches a using this example. So as usual, first I'm going to show you the graph of this rational function, which I have right here. So the graph of a rational function looks like this, and roughly speaking it consists of two or more pieces. Now, as we discussed a few seconds ago, and also we can see graphically that this rational function is not defined at x is equal to 2. The graph is broken at x is equal to 2, and also we don't see any value of this function corresponding to x is equal to 0. So this function is not defined at x is equal to 0 as well. The graph is broken at x is equal to 0, but the way it is broken at x is equal to 0 is different from the way it is broken at x is equal to 2. So we will discuss these two cases separately. Then you can see that except for x is equal to 0 and x is equal to 2, the rest of the real numbers are in the domain of this rational function. So broadly speaking, we will discuss three cases. That is the case when x is equal to 2, and then the case when x is equal to 0, and also the case of the rest of the real numbers. So let's first learn to determine the limit of a rational function as x approaches a number which is in its domain. So for this example, I have taken a number a on the x-axis, which is in the domain of this rational function. Now, determining the limit of a rational function as x approaches a number which is in its domain is exactly the same as determining the limit of a polynomial function as x approaches a, and which you can see graphically as well. So let's quickly see that whether x approaches a from the left or it approaches a from the right, in both the cases the values of this rational function approach the same point, which means that if a is in the domain of a rational function, then the limit of a rational function as x approaches a always exists, and it is equal to the value of f at x is equal to a. And this is called direct substitution property. So we have that if a is in the domain of a rational function f, then the limit of f as x approaches a is equal to the value of f at x is equal to a. So now let's quickly move to this point 2. That is, we are going to learn to determine the limit of a rational function as x approaches a number at which it is not defined. For example, this rational function is not defined at x is equal to 2. So let's see how to determine the limit of this rational function as x approaches 2. Now, Although you can see graphically that as x approaches 2, the limit of this rational function exists, and which is a number, say m. But we don't have f of 2. Function is not defined at x is equal to 2. So, which means applying the direct substitution property in this case is out of the question. So, we cannot write this limit is equal to value of this function at x is equal to 2. This is totally absurd. So now let's try to determine the limit of this rational function as x approaches 2 by applying the limit law that we had seen in the lesson number 6a. So I'm going to show you the quotient law, which I have right here, and which says that for any two functions gx and hx, if limit of gx as x approaches a and limit of hx as x approaches a exist, in that case, the limit of a quotient is equal to the quotient of the limits, with the condition that this limit is not equal to 0. So for our rational function, let's assume that the numerator is gx and the denominator is hx. And let's say the point A is x is equal to 2, because we have to determine the limit of this rational function as x approaches 2. So you can see there up to here we are fine, because gx, which is the numerator, is a polynomial, hx, which is the denominator, is also a polynomial. So the limit of gx as x approaches a and limit of hx as x approaches a exist, because in the previous lesson we learnt that the limit of a polynomial function as x approaches a always exists. Now the only thing here we have to check is that if this condition is satisfied. So let's check quickly. So the limit of hx as x approaches a is equal to the limit. Now hx is the denominator, so x squared minus 2x as x approaches 2. Again, determining this limit is not a problem because this is a polynomial function. So we can determine this limit by applying the direct substitution property as we learnt in the previous lesson. So this limit can be obtained by directly substituting x is equal to 2 in this expression, and which will be 2 square minus 2 times 2, and which you can see is 0. So the limit of hx as x approaches a comes out to be 0. That means this condition has not been satisfied. So in order to determine the limit of this rational function as x approaches 2, we cannot apply the quotient law. But the quotient law didn't work here doesn't mean that the limit of this rational function as x approaches 2 doesn't exist. We had seen graphically that as x approaches 2, the limit of this function exists and it is equal to the number m. So we have to think of something else in order to determine this limit. So we have this function as x squared minus 3x plus 2 over x squared minus 2x. Then we also know that when x is equal to 2, this function is not defined. So when you substitute x is equal to 2 in this expression, you'll see that f of 2 is 0 over 0. So substituting x is equal to 2 in the numerator makes it 0. So which means that x minus 2 must be a factor of this expression. Similarly, substituting x is equal to 2 in the denominator makes it 0. It means that x minus 2 must also be a factor of this denominator. See, this is just algebra. To make it more simple, if you subtract 2 on both sides of this, you will get x minus 2 is equal to 0. And it is this x minus 2 which makes this numerator and this denominator 0 when x is equal to 2. So now here we are going to apply what we learnt in the lesson number 2. Do you remember we factorized the numerator and the denominator depending on the numerator and the denominator to pull this factor x minus 2 from them, so that when we'll take the limit of this function as x approaches 2, we can get rid of that factor. Let's see how. So let's first quickly factorize the numerator and the denominator. So for that, in the numerator, I have x squared Now recall, how do you factorize a quadratic expression like this? So we will break this term minus 3x into two terms so that the sum of those two terms comes out to be minus 3x, and also the product of their coefficients is equal to the product of the constant term and the coefficient of x squared, which is 1 here. So let's see quickly. I can write this minus 3x as minus x minus 2x. So, and then we have this plus 2. So this is plus 2. So you can see that minus 1x plus minus 2x is equal to minus 3x, and minus 1 times minus 2 is plus 2, and which is same as the product of the coefficient of x squared, which is 1, and the constant term, which is plus 2. Now it is divided by x squared minus 2x. Now if you remember, we had already factorized it in the very beginning when we were determining the domain of this rational function. It's simple and its factors are x and x minus 2. So we see that this x minus 2 is the factor of this expression in the denominator. Now let's quickly finish the factorization of the numerator. So for that, I will take these two terms together and then these two terms together. So in these two terms, I can see that x is present in this term as well as in this term. So I can take x common. So I will be left with x minus 1 inside. And similarly, from these two terms, I'll take minus 2 common. So minus 2 is common here, and I'll be left with x minus 1 inside, and it is divided by x times x minus 2. So I'm not doing anything new here. These are just a few simple steps of algebra in order to factorize the numerator and the denominator. And we are almost there. So now here I can see that x minus 1 is present in this term as well as in this term. So I can write this as x minus 1 as common, and I will be left with x minus 2 inside. It is divided by x times x minus 2. Okay. So now we see that x minus 2 is present in the numerator as well as in the denominator of this expression. And it is this expression that creates a problem when x is equal to 2. Because in that case, this x minus 2 is equal to 0, and it gives us 0 over 0. So as we learnt in the lesson number 2, we cannot get rid of this x minus 2 and this x minus 2 when x is equal to 2. But if we take the limit of this function x squared minus 3x plus 2 over x squared minus 2x as x approaches 2. So first let me write limit as x approaches 2, and here as well limit as x approaches 2. Similarly, here as well limit as x approaches 2. So now x is not equal to 2 because now x approaches 2. That is, the values of x get closer and closer to this number 2. But x is not exactly equal to 2. So when x is not exactly equal to 2, then x minus 2 is not 0. So which means that this is not 0 over 0. This will be some non-zero number divided by the same non-zero number. So now we can cancel x minus 2 with this x minus 2. Why? Because in this case, x is not equal to 2. So all this has already been discussed thoroughly in the lesson number 2. So according to your learning needs, if you want, you may revisit the lesson number 2 for the detail. Now, what we are left with? We are left with limit as x approaches 2 of x minus 1 over x. We can see that x is equal to 0 is the only point where this expression is not defined. Because if we put x is equal to 0 here, this expression will be division by 0, which is not possible. So which means for the rest of the real numbers, this expression is defined. So it is also defined at x is equal to 2. That means x is equal to 2 is in the domain of this rational function. And in the very beginning of this lesson, we learned that if a is in the domain of a rational function, then the limit of a rational function as x approaches a can be determined by applying the direct substitution property. So, which means that this limit can be obtained by directly substituting x is equal to 2 in this expression, and which will give us 2 minus 1 over 2, and which is 1 over 2. So, finally, the limit of this rational function as x approaches 2 comes out to be 1 over 2. We see that although this function is not defined at x is equal to 2, its limit as x approaches 2 exists, and it is equal to 1 by 2. So this is how we determine the limit of a rational function as x approaches a number at which it is not defined, and it takes the form 0 over 0. Now, in this lesson, we saw how to determine the limit of a rational function if x approaches a number which is in its domain. And then we also learned to determine the limit of a rational function as x approaches a number where it is not defined and takes the form 0 over 0. Now we are only left to discuss the case of x is equal to 0. So in our coming lesson, we will learn how to determine the limit of this rational function as x approaches 0, when we will learn about infinite limits.